Well, hello 535, this is Dr. Keith Schubert, and we're now going to be talking a little bit more on some points on matrices, in particular on multiplication. So let's consider some vectors that are going in, and let's consider two vectors, let's say 3, 5 as one vector, and we will consider the vector 2, 1 as another vector. Now, in these two different vectors, there's two ways I can kind of multiply them. And this hits on a point from an earlier video I made about inner versus outer product. Let's say, for instance, we multiplied them with my row vector first. So, and I always kind of station mine when I'm doing multiplication. As I've mentioned in earlier videos, I always write my matrices this way, because then I can just line this and this up and multiply them. That's classic inner product. So I can just go 2 times 3 is 6, 1 times 5 is 5, so I have 6, and I have 5, and then I add them up to get 11. And that gives you your inner product. Now, that is classic inner product. That's the correct answer for it. Now, what happens if I multiplied them in a different order? 3, 5, and let's say I multiplied them by 2, 1. Now, if you notice what happens here, I end up with, again, it's compatible for multiplication. What I need is the number of columns here to be equal to the number of rows there. Well, that's certainly true. As a matter of fact, not only that, it's kind of trivially easy to do these as it goes in, because it's a bunch of very short, simple multiplies. And I've got 2 times 3 gives me 6. That gives me this element. To get this one, it's 2 times 5. That's 10. These ones are times 1. Now, if you notice when I was kind of multiplying through, I did them individually. Once you start noticing a pattern inside this, this one here is going to multiply 3 to get this. It's going to multiply the 5 to get this element. But that really means what we're doing here is we're saying this one is multiplying this whole thing, and I'm saying take 1, 3, 5 vector. Just like I took 2, 3, 5 vectors and got 6 and 10. So you can kind of treat them as entire vector areas. As a matter of fact, I could have rewritten this matrix here as 2 times 3, 5, and 1 times 3, 5. That really is what's going on with it. So it gives you kind of another way of looking at them. And we call this an outer product. Now, why do we care about this? Well, because we love mathematical obscurities. No, well, actually I do kind of love mathematical obscurities, but that's a completely different matter. This is actually a very useful thing to us. It's good to be able to recognize what things are when we're dealing with them, and sometimes multiplying them one way versus the other is more efficient or mathematically the correct thing to do. But let's consider a case where I now have a matrix, say 1, 2, let me actually write them so I can actually put them in my kind of multiply form. 1, 2, 3, 4, and let's say I'm multiplying this times 5, 6, 7, 8. Now, I can do the classic method we have done up until now, right? What I call the inner product multiplies. Right, where to get this first element, the 1, 1 element here, I do 1 times 5 gives me 5, 3 times 6 gives me 18, 5 plus 18 gives me 23. And to get this element, I go 2 times 5 is 10, 4 times 6 is 24, add 10 and 24, and I get 34. And then we can, of course, continuing this process on to get the back elements here. I've got 1 times 7 plus 3 times 8. Right, so I have 7 plus 24, and that gives me 31. And then I've got 2 times 7 is 14, 4 times 8 is 32, and so then 14 plus 32 gives me 46. And we have our answer. Now, another way I could have looked at this, because what I did is I did 4 individual inner product multiplies. This one times this one to get here, this one times that one to give this one times this one to get that, and this one times that one to give me this. What if instead I had taken the same thing, got to make sure there's enough room here, looks like I might be able to fit. 1, 2, 3, 4, 5, 6, 7, 8. What if we took a different thing to notice? And we noticed that when we do our lineups, this always multiplies this. And this one always multiplies these. And there's no way to cross between them. I could kind of look at it as 2 outer products being resulted in here. One outer product is 1, 2 times 5, 7. Now this is really easy to kind of write down because all I'm doing is 5 times 1, 2. Well, that's 5, 10. And 7 times 1, 2, well, that's 7, 14. And then I have 3, 4. And I'm multiplying that by 6, 8. And I'm doing now the same exact thing again. Now I'm doing 6 times this. 6 times 3 is 18. And times 4 gives me 24. And 8 times 3 is 24. And 8 times 4 is 32. And then I'm taking these 2 right here, because that's what we said. It's this one, and we just add them together. That's what we've always done, is we've added the results of these to these. That means I take both of these together and I sum them up. So I just go 5 plus 18 is 23, 10 plus 24 is 34, 7 plus 24 is 31, and 14 plus 32 is 46. And you will notice you get the same amount. Now, this one was pretty easy for a human being, which is exactly why we as human beings use it over and over and over again. This one right here was, it's kind of easy to do at the end, but the early parts required scratch space and all kinds of other stuff, and seemed like a lot more work. So as a human being, this is a lot easier. This is a good time for me to introduce one of those great kind of folk theorems in numerical computation and really truly computer science in general. What's good for a human being is usually not as good for a computer, and vice versa. Turns out often this one is quite useful to us to do things. Now, neither one of these is tremendously better for human beings or tremendously worse, so therefore there's going to be times when both are going to be useful for us in computers. There will be slight advantages to this method, though, under certain circumstances, and since most people don't think of it, it often puts them at a disadvantage when trying to solve these type of problems. So please keep aware of the inner versus outer product form of writing it. They give you the exact same answer. It's just a trade-off of how you do the computation and how do you distribute the data and where does the parallelism come. So, these type of things become kind of issues for us of what would we like to have happen. So that kind of summarizes up what I wanted to let you see for some other ways of looking at multiplication. I hope this kind of helps, that it will come up later on inside of our coursework. So thank you very much, and we'll talk to you soon.